Hello. How's it going? It's going, yeah. Yep. It's just a question of the rate at which it's going, right? Yeah. So, might as well call this meeting to order then. You guys done your midterms yet?
Yeah, but we've got a lab.
You've got a what?
A lab.
You got a lab. Well, you know. It is what it is, I suppose. Yes?
If there's a snow day tomorrow, what does that mean for people with tutorials tomorrow? Just virtually demonstrating?
So, yeah. Well, actually, no, we can't demonstrate the tutorials virtually because if they close the school for a snow day, apparently that means all classes are kaputski. So we can't hold lecture, we can't have a tutorial or a lab or what have you. So we will invoke it gets demoed after the break. Right? Good. Are they calling? Like, how much snow are they calling for? 30? Here in Hamilton? 20? All right. All right. I was just about, like, I'm this close. I'm this close, winter. Like, yeah. That doesn't help me with my shoveling in the morning. Yeah, normally it's like if the snowfall is heavy and it's kind of the like 3 to 6 in the morning bracket, that's normally the best predictor of a snow day, you know?
It's going to keep her off around there.
Yeah. We'll see how it goes. We'll see how it goes. I mean, who wouldn't want a snow day the Friday before the midterm recess? Am I right? Let alone all of the inconveniences it causes for professors. So, anyway. So, last time we talked about real-time clocks, and we pretty much finished that topic off in one go. So now we are going to move on to our next topic. This is not lab-related, but it is still material that we have to cover for accreditation purposes, actually. So it is a component of the curriculum for this course that we discuss some business metrics and some, some product business stuff. This, if you're in, how many people here are in the management stream?
I don't think
Like 2 people. Hello, management people. So this will probably be not news to you guys, but you know, the particular applications of it to embedded systems might be of interest to you, you know, seeing as that's the hypothetical career path you're on. So, we're going to talk about products and how to design a product that doesn't flop, or at least what the important metrics are. So, what's the difference between a hacker and an engineer? Morals? Well, I mean like hacker as in, do they call them makers now? I can never keep up on the terminology. People who hack things together. Technical knowledge? No, I would say that a lot of the hackers have the same level of technical knowledge as an engineer.
Well, engineers paid 70 grand in tuition fees.
Yeah, there they go. 70 grand in tuition fees, that's one big difference, yeah. So, when a maker, or a hacker, or a person of that nature, is creating a solution to a problem, all that's pertinent to them is how the degree to which their solution solves the problem at hand. does it work? That's their primary consideration, right? An engineer needs to optimize design metrics, right? An engineer works for a company. In order for that company to continue existing, the product needs to make money. In order for the product to continue, in order for a product to make money, it must satisfy certain constraints related to the marketability of that product, right? And we're going to review, sort of at a fairly high level, some of the design metrics that are important if you wish your product to actually be saleable. So, any questions about that so far? I probably asked too early. It's like, introduction. Questions? Yeah. Anyway, so the particular, like, you'll notice that this is like, this course being probably the first like true mechatronics course that you guys are taking in your degree program. We're pulling in a lot of stuff from a lot of different places, right? Sometimes we're talking software, sometimes we're talking hardware. Actually, most of the time we're talking hardware, and you guys are expected to just know the software somehow. Because, you know, reasons. I guess teaching software is difficult or assumed to have occurred already. But, so, as mechatronics people, you are uniquely positioned to be able to manage these metrics across what would ordinarily be multi-discipline areas, right? It's like you are the people who will best understand the trade-offs between hardware and software, right? Like, it's up to you to know when a solution to a problem is better implemented as an IC, as a custom circuit, or as a piece of software, right? So, good. Embedded systems, like, as we've examined before, embedded systems is a very, very broad category of objects, right? It's everything from children's toys to wristwatches to smartphones, right? So, generally speaking, among all of these applications, there's, with the possible exception of smartphones, because they've kind of exploded in recent years and are most people's general purpose processing devices these days. So let's not consider smartphones for the moment and go more into like the, you know, the nuts and boltsy type stuff. Generally speaking, embedded systems are designed to perform a single function, right? So generally speaking, we don't need the idea of reprogrammability inside of an embedded systems environment, right? That's that's why I'm excluding cell phones, because you can like load a new software onto a cell phone, that means that it's not, like, it's a reprogrammable environment. You know, for some of them, you can even like load a new operating system onto them, and that sort of thing. Generally speaking, embedded systems have very tight constraints when it comes to such aspects as the cost, the power consumption, and the size can be a big issue as well, how quickly it can execute its functions, these types of things. Like, if you think about, like, take, for example, pedometers, right? Pedometers are a class of product which has seen a fair amount of development over the last, you know, decade or two. Anybody remember what like a pedometer from the year 2002 looked like? Yeah?
Like the ones that they gave out at McDonald's, that like you could shake them and the steps would increase.
Yeah, like that one. You'd clip it onto your belt and it was like a thing like that was about that big, right? It's like, those were popular for a period of time. My mom bought one. She used it like maybe for a couple of weeks, but she bought it, right? And it doesn't matter if it's only used for a couple of weeks, the point is she bought it. So, as time went on, pedometers became increasingly miniaturized to the point where you get something like the Fitbit. Like if you think about the amount of space there is in a Fitbit, how much space is that for electronics? Not a whole lot. You couldn't it's difficult to imagine having space for like a large oscillator inside of the housing of a Fitbit, right? So, as time went on, the market trend in pedometers was more towards smaller devices which could be embedded in things like wristwatches, right? So, the size of the overall circuit board design, that became a metric which came to dominate the market. To the degree that you met that metric, your device would sell. And one of the reasons that Fitbit did as well as it did is because it managed to get the miniaturization really, really tiny, right? Even at the cost of functionality, they miniaturized it, and that was what sold it, right? Unless that wasn't what sold it, I'm sort of throwing conjectures around here, but at any rate. So, if these things have internal batteries, generally speaking, one of the important metrics for a person who's buying one of these devices is like, how long does the battery last, right? If you remember, the Nintendo Switch got pilloried because its battery life is really not great depending on how complicated the game it's running is, right? Still sold like hotcakes because it's a Nintendo device, but but yeah. So, and of course, our embedded systems have to be reactive and real time. So, this is essentially, they must be computing devices which poll inputs and produce outputs with a reasonable update rate, right? The device is only as sensitive to its environment as the sensors that you put into it, right? And it's only as fast as the power of the processor that you put into it. But of course, the more powerful the processor is that you put into it, the more power it's going to consume, which might drain your battery life. So a lot of these things are trade-offs. Many, 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 many trade-offs. So, generally speaking though, in embedded systems design, notable delays are not really what you want, right? You want things to react quickly. Any questions so far? Okay. So, the obvious design goal of any piece of tech, if you want to phrase it that way, is to fulfill the specifically outlined requirement of the device. A Fitbit must track your steps, optionally heart rate. A children's toy must serve to amuse a child. Your Game Boy must be capable of playing Tetris. All of these types of things, right? I guess that is also a toy that's meant to amuse a child, but you know what I'm talking about. So, but this is just the obvious design challenge. The real meat of your future employment really is, can you get the thing to perform its intended functionality while at the same time optimizing all of these design metrics that we've been talking about. So, design metrics are, of course, measurable features of a system's implementation. If it's not measurable, then how do you know if you've improved it, right? And this optimization between the different design metrics is the key challenge of design itself. So, here are an incomplete list of some common metrics that you might be interested in, right? Notice how the very first one that's listed is unit cost, right? Of all of the design metrics, unit cost is the one that will have the most pronounced effect on the cost to the consumer of purchasing the item. The cost of purchase of the device is possibly the most powerful indicator of whether or not that thing is going to sell or not, right? Like, price is super, super, super important. And all of you know this, because all of you, if you're in a grocery store and you have like 2 different brands of bread, and one is 20 cents more expensive than the other, and they look like they're equivalent loaves of bread, how many people will arbitrarily pick the more expensive bread? Right? Unless you've like read the nutrition information and be like, oh, well, this is bread that has very high levels of riboflavin, and I need that in my diet for some reason, so I will choose the more expensive bread, even though I know it's more expensive. Consumers are extremely sensitive to price. So the price of the product, of course, is a function not only of the unit cost of the manufacture of each device, but the amount of money that it costs to develop the device in the first place. This is known as the non-recurring engineering cost. So this is the amount of money that you have to pay your engineers in order to develop the prototypes. It's the amount of money that you have to pay your design staff to design the manufacturing process for your device. Anything that you have to pay up front that does not scale with the number of units that you produce is your non-recurring engineering cost. Notice the word non-recurring. So, in order for a company to actually make money on something, the non-recurring engineering cost must be covered. The unit cost must also be covered. And there needs to be some amount of money that the company actually makes from the sale of the product. Otherwise, how are they going to pay their overpaid CEO, for example? Not that CEOs are always overpaid, but you know what I mean. So, and we're going to get into like cost analyses a bit more as we go through this. So, another common metric is the physical space required by the system. Again, there is a strong trend towards miniaturization. This trend of miniaturization has been ongoing basically since the development of electronics itself. And I don't know. I think I've already hit that point pretty hard. So size matters. Performance also matters. The execution time of the system. If you have a let's say you have like a little Kindle or a Kobo device, like an e-book. These were popular a number of years ago. I'm not sure how many people have an e-book, like either a Kobo or a Kindle or something like that. Yeah, like maybe a half dozen people in the audience. They're not as popular as they were a number of years ago. I remember in my family, we bought Kobo, which was sort of the Chapter's Indigo version of that device. The thing wasn't, like the performance on the thing wasn't fantastic because there was a noticeable delay when turning pages, right? And it's like, yeah, okay, you don't need to turn pages that much, I suppose, but you kind of do. So, something like that, which is like a minor annoyance, will really like hurt your customer reviews on Amazon, for example. which is like the modern equivalent of what we used to have, which was word of mouth. It's like, well, you know, the thing is okay, but it's kind of slow, you know. You don't want your device to be noticeably slow. They just didn't give it enough horsepower, right? But the thing about the Kobo is that the battery life of it was extremely long. Like the thing would go for, you know, it would, I think you could go for like 3 weeks between charging on that thing. And it was also like they had used a special type of screen which only requires electricity when it updates in order to further the power savings on the device. And then, of course, they killed all of their wonderful battery optimization by introducing a backlight in the next generation. But you know, so yeah. So that kind of leads us into power consumption. Since embedded systems will, in pretty much all, most or all cases, be running off of a battery, power consumption of the system is directly proportional to the amount of battery life that you can expect from it. The only way to compensate for a higher power drain device is to put a bigger battery on it. Bigger batteries require more space, and they also they have greater weight. And in the same way that size is a important design metric, weight is also an important design metric. You know, nobody wants to lug around like this gigantic brick of a thing unless like there's a very good reason for it. Like, for example, due to certain instances that, certain problems that I had last couple of weeks ago, I found one of these portable battery banks on sale at Staples. $30 on normally $50. It was a pretty good deal. But like this thing, like man, this thing could be used as a murder weapon, you know? And it's because it's filled with batteries, and batteries are heavy. And it's like, I'm okay with the weight of the thing because pretty much any battery bank that you get is going to be like that, right? But like if this were the type of power supply that you required for your cell phone regularly, like they wouldn't nearly have taken off the way that they have, right? Like if you imagined like putting a screen on this thing and making it into a cell phone, it wouldn't work, right? Question?
I think Energizer tried to do that.
Did they?
With a battery life of 5 days, and the phone was like this thick. It was pretty bad.
Yeah, because like, who wants that, you know? Yeah, like, I think cell phones are like absolutely like, they're like the quintessence of designing for size and weight, you know? Although, interestingly, like one of the things they've been doing lately is like getting like larger as time goes on. I don't know, I think they've kind of plateaued for the moment in terms of like a screen area, but you know, at any rate. So another metric which is very important for embedded systems from more of a design angle is flexibility. How difficult is it to modify the system, right? So this doesn't necessarily just mean reprogrammability of the device itself, although that can be a large component of it, right? It can also mean how easy is it for you to like throw another IC on top of the existing design, right? Going back to the Kobo example, how difficult would it be to take the existing design and throw a backlight into it, right? Because, you know, I can tell you that the Kobo with the backlight was pretty much exactly the same, exactly the previous Kobo, but with a backlight. So it's kind of like the initial prototype will hopefully take most of the cost because it costs less money to iterate on an existing prototype than it does to just, redo the whole thing from scratch. This is also how cars are done, generally speaking. Like, they don't, like, they'll say, the 2022 Honda Civic, but really it's the same Civic that they've had since, 2008, but with a few additional bits and bobs that have been modified and tweaked. Question?
So would not making something flexible really just improve our job security?
Yeah, at the cost of the performance of your product in the marketplace and the viability of your company. So yes, that's also a trade-off. Yeah. So you often hear stories from the '80s of like programmers who wrote code which is so like obscenely intricate that they're the only person on Earth who knows how it operates, and thus like there's. I remember a story about a slot machine that was like a video slot machine that was written in assembly code, and like the management had a problem with the coder who wrote the assembly program because he was an asshole, and he just left the company, and they had to throw out the whole thing because no engineer could understand what the hell was going on with his code, right? So yeah, I mean, I think I like Google's old motto of "Don't be evil." But yeah, so actually, it's kind of interesting. Like back in those days when like assembly was still very popularly used to program stuff because there wasn't a lot of options. It's interesting because like programmers didn't really get credit for anything. Like programming itself wasn't really considered a proper job to some degree. And so like if you take a look at like some of the old Atari games, they're often like they're not credited with the people who actually wrote the program because Atari was like, well, no, it's an Atari game, you just work here, right? So it's interesting to see how like as things have gone on, programmers are actually now getting credit more for the things that they produce. But anyway, any other questions? Cool. Is this like a nice fluffy lecture to end the week on? Yeah, good. So, to continue, time to prototype. The time that you need to build a working version of the system. This can be a very important metric, especially for any of you who might have any pretensions of starting like a crowdfunding campaign or a Kickstarter or anything of that nature. It's like, generally speaking, in order to get funding to fund the development of your device, you'll often need a prototype of that device. The longer it takes you to develop that prototype, the longer you have to go without any funding. And going, like pouring your heart and soul into a project when you're not getting any money for it, in the expectation of money that may never actually materialize, is like, simultaneously hell and most, independent developers' lives. So, indie games especially. Time to market is the time required to develop the system to the point that it can be released and sold to customers. Obviously. So time to market is actually a critical, it's a critical metric in competitive marketplaces. Generally speaking, like this is typically how things go, right? And this is kind of like tragic at the same time as it's like the way that things work. Generally speaking, the person or company which comes up with a like brilliant innovation is not the person who makes money on it, right? You come up with a brilliant innovation, you release your product, other companies look at your product and they're like, oh, that's a pretty cool thing. Like you'll get looked at by all early adopters, then it's a race by the major manufacturers to see who can develop the look-alike to your very innovative product and get it out fastest so that they can like capitalize on the development of your sort of catalyze on the the market buzz that's being produced by the new innovation, while at the same time actually having the market the money behind them to be able to succeed in the marketplace in a way that you'd never be able to hope to. Have you ever wondered why during a particular holiday season there'll be like 2 different brands of like coffee maker that are both like the pod type coffee maker that both arise, it seems, simultaneously? It's because they were both looking at the same source and they were both trying to beat each other to the market because they saw a market opportunity for it. Right? Make sense? Time to market is very important. The less your time to market is, the more you can beat your competition to the market, which, if you can get your product to the market first, generally speaking, the early bird gets the worm. So, maintainability is also fairly important, generally of concern to software systems more than hardware systems, because as we discussed last lecture, you can't patch hardware. You can patch firmware, but you can't do any. Once the circuits are laid in, my friend, that is what it is until it dies. So maintainability might be something like: did you put an access port on your device so that it can have its software reflashed? Did you put a factory reset button on the back of it? These types of things. The ability to maintain, modify, or correct the behavior of the device. Also, correctness, safety. There are many, many of these design metrics, but this is like a sufficient description for the time being, I think. So, expertise with both software and hardware is needed to optimize design metrics. Ordinarily, when you talk to people who are actually industry professionals, you'll have an expert in software, you'll have an expert in hardware. Only rarely do you have someone who is an expert in both software and hardware. This is this is the theory behind which your entire degree program was created, right? So, in order to be able to optimize such all of these design metrics, you as the designer have to be able to pick out which problems are better addressed in software versus hardware. What the implications of that for the design metrics would be, and et cetera, et cetera. Questions? Okay, good. So generally speaking, most of the time, when you are selling a product, there's a fairly reliable graph or function that your sales end up looking like, right? So generally, it's like, if this is time, and this is sales, starts off slow, ramps up to some peak, and then it sort of has an exponential tail off, right? And you might throw like a peak in here, here or there if the thing goes on sale, right? But in general, if you took like the average and if you weren't putting the thing on sale, this is what you're looking at, right? So, generally speaking, when you have a product, there is a certain window during which you will make the majority of your sales. The duration of the market window and the frequency of sales that are made during that market window are going to determine the financial viability of your product. Because while it might be nice to still be selling the thing, 4 years from its release, you'll probably not be, relying on that income to fund your operation is not going to be an effective strategy. Yeah. Good. So, so generally speaking, within this, within the embedded systems world, you have, generally speaking, 8 months to get your product to market. Delays can be extremely costly, particularly if there are competitors in your field, which there will be usually, right? So, good. So this is a simplification of the previous graph, so that so that we don't have to do calculus, basically. Because who wants to take the area under that thing, right? Much easier to work with triangles. So, if you keep in mind that the market window itself is, this is a fixed, this is like an artifact of human psychology, right? If you miss the window, say you have a delayed entry into the marketplace, you're just simply not going to reach the same peak as if you had, right? To some degree, what your peak sales are is it's a function of how many sales you had so far, particularly if you can catch word of mouth, right? It's like the more popular something is, the more popular it gets, right? It's kind of like a Pareto effect, actually. Have you guys heard of the Pareto distribution, or the Pareto function? No? Yeah? A little bit? Essentially, it's something. So if for example you take an organization like a business, right? The square root of the number of the people in that business do half of the work in that company. And then if you take that number of people, the most productive people in the company, take the square root of the number of them, that number of people do half of the work of those people. It's a natural law. It controls not only productivity across human endeavor. It's like how much food farms produce is governed by the same relation. The size of cities is governed by the same relation. The size of trees in the rainforest is governed by the same relation. It's a result of a sort of, the more something has, the more it accumulates, right? It's also it's even applicable to the mass of stars, right? So, essentially, this early period right here, that's absolutely critical. You need to get as many sales in this period as humanly possible. The launch of the product is the absolute most important time in that product's lifespan. And everybody knows that, but maybe now you have a better understanding of why. So, so if we imagine, in this simplified diagram, that we have the peak revenue, say, in some amount of time W, and then the market fall occurs after after twice that amount of time. Delayed entry into the marketplace will result in peak revenue being less than it would have been. So basically, you're losing all of this area, which is sales, right? And as you can see, in this particular case, the delay is not that long, but the amount of sales lost is practically half of it. right? This can have a huge, huge impact on the financial viability of the product, right? So when your boss, like 10 years from now, when you're working for a company and your boss is on your ass to get the product out, it's like, I need it this week. It's like, this is why. It's because your job depends on it getting out that week, right? Any questions? Yeah.
How would like pre-orders factor into this?
So, I can only speculate, but I can provide you some of my speculation. So pre-orders or pre-sales, it depends on the market, but normally the purpose is to build hype for launch, right? It's like, essentially, well, to some extent what you're doing when you're doing pre-sale is it's like you've got two of these curves going on, right? Like you've got a certain bump for like the pre-orders. Maybe it would look like much like that, because say like this is the release of a trailer, right? Then you have product launch. So the number of adopters of this thing will already be up here, right? So essentially, rather than starting like this, you're already starting like that, right? So because you are starting up here rather than down here, and the peak sales are determined by how many people, or at least heavily influenced by how many people actually have the thing, because they're sort of generating word of mouth and leaving reviews of your product on whatever it is. It's an effective strategy for achieving a higher peak sales. This is all conjecture on my part, but I imagine that's what's going on with pre-sales and pre-registration and all of that stuff. Generally, like personally, I will never pre-buy anything, because it's like, I'm not giving you my money until you give me the thing, and that's just one of my principles. But you know, unless they're giving away like a cool poster or a figurine or something, you know, like I want my pre-order bonus. Anyway, so if you were to take this and derive mathematical equations for the amount of money that you're losing based on this simplified triangular model of something that's actually, you know, not triangular, your on-time sales, right, will be the area of this triangle plus the area of that triangle. So it's, you know, half base times height. So base is W, height is peak revenue, and then, you know, W again and peak revenue again. The loss that you incur, the base of this triangle shrinks to W minus D, right? And then, well, it also depends on how much it, you know. This is kind of a strange example, actually, because it seems like it's missing a couple of variables, like peak revenue from delayed entry. Where's that represented as a variable, right? Well, at any rate, the point is delays are costly. I won't require you to calculate this on a quiz or anything. Okay? Question? Yeah?
So why would like delaying it by 1 day make that curve? Does the whole curve just kind of get shifted? Or is it kind of with the competitors, and if they release their thing first?
So,
or is it like expectations of other people, like it's coming on this day and it loses some height, or?
So, it's like, I can only answer an analogy, right? Think of like the desirability of a product in the marketplace as being like momentum, right? Like, the marketing department's job is to build momentum for the product, right? Hypothetically speaking, the peak of that momentum needs to coincide with the release of the product so that everybody gets out there and buys it immediately, right? But people will lose interest in the product over time. New products will be released, and it'll just kind of fade out of the mind's eye of the public, right? So generally, like, you have to consider market competition not just like your direct competitor in the marketplace, but you're also competing for the attention of human beings versus anything else in the world that they might want to be, that people are trying to sell them, right? So it's like, you know, for example, the Instant Pot, like, only has a specific window during which people are interested in buying an Instant Pot, you know, and it starts to trail off precipitously when they realize, wait, isn't this just a pressure cooker, you know? It's like Instant Pot. It's like, yes, it's a pressure cooker. We've had pressure cookers for years, but, you know. So, like, the window itself is determined by human psychology, not the release of the product, right? So, like, anytime people want to buy your product, but your product isn't actually released, you're losing momentum, right? And you're losing sales. And you may not make those sales back because by the time your product, like, by the time the person who wanted to buy your product on day one but couldn't gets around to wanting your product again, they may not even, because, you know, the next thing will have come along, right?
So that's like kind of an extreme example. Like Instant Pot wouldn't have probably lost 50% of their revenue if they released it one day later.
No, in this particular model, this is like, if you imagine like your window is 2 months, right? And it takes you 2 weeks to get the thing out, right?
Yeah.
Like we're not talking about delays necessarily of like on the scale of hours, right?
I just didn't know. Oh, that's decent. I thought that was like kind of a weird scale. It was like day, week, 2 weeks.
Oh, yeah, I don't like this graph at all.
I thought it was trying to say that it was 1 day late and it lost 50% of the revenue.
Oh, I'm going to assume that D is a variable. It stands for some number of days.
Yeah.
It's delayed.
Delay? Oh, yeah, okay. D means delay, and it's not days. Yeah, okay. Thank you. Any other questions? Okay. So associated, so you can kind of break the cost of a product into the non-recurring engineering cost and the unit cost, where the total cost of the entire product run is the non-recurring engineering cost plus the unit cost multiplied by the number of units. Now, how many of you have been on DigiKey ordering parts? Fair number of you. How good are the discounts when you start ordering in bulk? Yeah, right? So, like, actually, just quickly, let's take a look, eh? Or, no, I need something with internet. Anyway, I'll just recite from memory. So, if you have like an IC, like say you have a real-time clock module or something like that, the economies of scale on electronics are absolutely incredible, right? Like you can literally acquire a part for 1/100th of the price if you're ordering in sufficient quantity, right? So the unit cost is dependent on the number of units that you're producing. Again, especially in electronics. So well, I don't know, it's 6:19, so Anyway, I'll show you these graphs quickly, and then we can go. All right? So if we have 3 products, right? One with a non-recurring engineering cost of $2,000, $30,000, and $100,000, and unit costs of $100, $30, and $2, you can see that if you're only making, 400 of the things, then technology A is what you should be going for. But the more of it you make, the more heavily favored higher engineering costs are and lower unit costs are, obviously. And again, the economies of scale compound this effect, right? These graphs are actually pretending that unit costs are stable with respect to the number of units sold, but that's not actually the case. There's a big difference between buying 10,000 of something and 10 million of something in terms of the cost. But yeah. Anyway. Have a good break. Woo! Are you guys having a break or? Yeah.